And now we have examples part 2 of our discussion on temperature and heat. First, we have sample problem number 3. A copper slug whose mass is 75 grams is heated to a temperature of 312 degrees Celsius. The slug is then dropped in a glass beaker containing 220 grams of water. The glass beaker has a heat capacity of 45 calories per Kelvin. The glass beaker and the water both have an initial temperature of 12 degrees Celsius. The specific heat of copper is given 0.0923 calories per gram Kelvin. Assuming the water does not vaporize, determine the final temperature of the system at thermal equilibrium. So we have 3 objects in the system. You have the copper slug, mass is 75 grams. Then you have the glass beaker, no mass is provided. Inside the glass beaker, you have water. Mass of the water is 220 grams. The temperature of the copper slug is given 312 degrees Celsius. So let Tc be 312 degrees Celsius. That's the initial temperature of the copper slug. Initial temperature of the glass beaker and the water are the same, 12 degrees Celsius. So Tg is equal to Tw is equal to 12 degrees Celsius. Initial temperatures for the glass beaker and the water contained in the beaker. Given is the specific heat of copper. Let that be small cc, specific heat of copper, 0.0923 calories per gram Kelvin. Now, no mass of the glass beaker is provided. Instead, the problem gives us the heat capacity of the beaker itself. Remember that heat capacity is property of the object itself, not the material making up the object, but the object itself. So the heat capacity of the glass beaker, not the glass comprising the beaker, but the glass beaker itself, the heat capacity is 45 calories per Kelvin. So capital C, heat capacity. Water inside the glass beaker, we know the specific heat of water. Cw, specific heat of water, we know to be 4,187 joules per kilogram Kelvin. This is equivalent to 1 calorie per gram Kelvin. The system reaches thermal equilibrium, meaning all objects in the system have the same temperature, they have the same final temperature, and that's what we are looking for, TF. The objects in the system will interact. Objects will gain heat energy. Some objects will lose heat energy. The total energy change is equal to 0. Conservation of energy. Summation of MC delta T plus summation of plus minus ML is equal to 0. Again, conservation of energy in terms of heat energy. So, look at each object and determine if each object will have a temperature change. So, we have 3 objects. We have the copper slug. Does it does the copper slug undergo temperature change? We have water inside the beaker. Will the water undergo temperature change? The glass beaker. Will the glass beaker undergo temperature change? The same goes for phase change. So ask yourself, look at each object, and determine if each object will undergo phase change, if each object will have plus minus ml. Now, looking at the temperatures involved, 12 degrees Celsius, 312 degrees Celsius, the temperature is low enough that no phase change is going to occur. Particularly, the problem tells us, assuming that the water does not vaporize, boiling point of water, you will recall, is 100 degrees Celsius. So that's within the 312 degrees Celsius range. But the problem tells us that let's assume that the water does not vaporize. So no boiling of the water will happen. Glass beaker is solid. It will take a very high temperature for the glass beaker to melt. And the same goes for the copper slug. So, no phase change will happen. So, no plus minus ml, only temperature change. So, each object will have temperature change. So, for water, we have MW, CW, delta T, final temperature TF, minus initial temperature of water. Now, the glass beaker, we don't know the mass of the glass beaker, but what is provided is heat capacity of the glass beaker. So instead of mc delta T, we use the other equation for temperature change. The one that uses heat capacity instead of specific heat. And that is C delta T. Heat capacity times delta T. So Cg delta T. Tf minus Tg. Final temperature Tf minus initial temperature of the glass beaker. And then we have the copper slug. So Mc delta T for the copper slug. Mc Cc times delta T for the copper slug. That's final temperature minus initial temperature of the copper slug, equal to 0. We are looking for Tf. So isolate Tf. We get Tf is equal to Mw, Cw, Tw plus Cg, Tg plus Mc, Cc, Tc divided by Mw, Cw plus Cg plus Mc, Cc. All these values are known. We are able to calculate the final temperature of the system. And plotting in the values, we get Tf is equal to 292.787 Kelvin or 19.637 degrees Celsius. Next, we have sample problem number 4. How much heat must be absorbed by ice of mass 720 grams at negative 10 degrees Celsius to take it to a liquid state at 15 degrees Celsius? So, mass of the ice, let that be M, 720 grams. Convert to kilograms. Initially, the ice is at negative 10 degrees Celsius. So, initial temperature Ti is negative 10 degrees Celsius. Convert to Kelvin. Final state, the ice has melted. It is now in liquid state. You have water, melted ice at 15 degrees Celsius. So, final temperature Tf is 15 degrees Celsius. Convert to Kelvin. The ice will melt. The melting point of ice is 0 degrees Celsius or 273.15 Kelvin. We know the specific heat of water to be 4,187 joules per kilogram Kelvin. We also know the specific heat of ice, 2,220 joules per kilogram Kelvin. The ice will melt. We need the heat of fusion of ice or heat of fusion of water. LF, we know to be 333,000 joules per kilogram. And we are looking for the total heat needed, Q total, that will convert the ice at negative 10 degrees Celsius to a liquid state at 15 degrees Celsius. Now, the process is you have ice, solid H2O at negative 10 degrees Celsius. If we add heat to the ice will increase in temperature, will undergo temperature change until it reaches the melting point temperature of ice. So the temperature change of the ice will be from initial temperature, negative 10 degrees Celsius, to melting point temperature of ice, 0 degrees Celsius. The heat associated with the melting of the ice is Q, with the temperature increase rather of the ice is Q ice. Now the ice is at the melting point temperature. Any heat that we add to the ice will melt the ice. You have Q melting. Once the ice is melted, it is now water. Water at 0 degrees Celsius. Final state is 15 degrees Celsius, so we are not yet at the final state. So we continue adding heat to the melted ice, to the water. That will increase the temperature of the water. It will increase from 0 degrees Celsius to the final state. The temperature will increase until we reach the final temperature, 15 degrees Celsius. And the heat associated with that temperature change is Q water. So Q total is equal to Q ice plus Q melting plus Q water. So to get Q total, we need to get the individual heat associated with each step in the process. So first, we have Q ice. Q ice is heat associated with the temperature change of ice. So Q is equal to mc delta T. Q ice is equal to m of the ice. C ice delta T ice. Delta T ice is temperature change of the ice. That's from the initial temperature until we reach the melting point of the ice. So T melting. So T melting minus T initial. We know all these values. We are able to calculate Q ice, 15,984 joules. Next, we look for Q melting. Q melting, heat associated with melting is simply positive MLF. So Q melting is equal to MLF, mass of the ice and heat of fusion of the ice. We know these values, thus we are able to calculate the Q melting of the ice, 239,760 joules. Lastly, we have Q water, heat associated with the temperature change of the water from 0 degrees Celsius to the final temperature of 15 degrees Celsius. Q water is equal to mc delta T, so mc water delta T water. Mass of the melted ice, mass of the water, since it just came from the ice, mass of the water is also mass of the ice. Delta T water is change in temperature of the water. We have just mentioned that. From 0 degrees Celsius to the final temperature TF. So delta T water is just TF minus T melting. And again, we know these values. We are able to calculate Q water to be 45,219.6 joules. So Q ice, Q melting, Q water, adding them all together, we have Q total 300,963.600 joules. The heat needed to turn the ice at negative 10 degrees Celsius to melted ice to a liquid state at 15 degrees Celsius. And that's it for now. That's it for our discussion on examples part 2. We'll continue our discussion on temperature and heat in the next video. In the next video, we take a look at the concept of modes of heat transfer, beginning with thermal conduction. So again, that's it for now. Thank you for watching.